Hi Space Cats, I'm Dr. Maggie Lou, welcome back to my channel. It feels like quite often now we hear people say Einstein is right again. But is Einstein really right about gravity? In this video, let's talk about gravity and modified Newtonian dynamics. Let's begin. In 1687, Sir Isaac Newton devised his law of universal gravitation. His second law tells us that force F equals mass m times acceleration a. Here on Earth, to calculate the force due to gravity, we use a gravitational acceleration of 9.8 meters per second squared. For over 2 decades, Newton's theory served its purpose well, and it still does today. Students learn Newton's theory in school and can successfully execute science experiments to measure Earth's gravitational acceleration. Newton's theory excels at describing gravity at our local scales here on Earth and even our planets. Newton's predictions correctly predicted the existence of Neptune. According to Newton's theory, the planets move around the Sun in elliptical orbits. However, these ellipses are not fixed. They move slowly in a way that's called a precession. This precession is something that is more pronounced in regions of stronger gravity, like Mercury, which has been observed. Newton's theory cannot explain the precession, and the predicted angular deflection of light rays by gravity that is calculated by using Newton's theory is only 1/2 of the deflection that is observed by astronomers. About 250 years later, Einstein gave an explanation of gravity and developed a mathematical treatment of gravity that could explain some of the inconsistencies between what we observe and Newton's laws. You see, Newton explained gravity as a force, but Einstein explained gravity as geometry. The curvature of space-time g is encoded into a tensor t that describes the distribution of mass energy. This theory of general relativity is in much closer agreement with astronomical observations. Einstein's special relativity, a special case of general relativity for a flat spacetime, is based on the theory that nothing can travel faster than the speed of light. In special relativity, we can write a relativistic correction to Newton's second law by including an extra term. Here, we still have the original terms from Newton's equations, force F and acceleration a, but m0 is an object's rest mass, and the latter term we have speed of light c and speed v. When the speed of an object v is much smaller than the speed of light c, this latter term goes to 1 and we recover Newton's second law, F equals ma. It turns out that Newton's gravity is an approximation, but rather an extremely accurate one. It was accurate enough to put a man on the moon and to space travel around the solar system. But Newton's theory of gravity is not accurate enough to make our GPS systems work. The locations predicted by a GPS system that do not take into account Einstein's theory will be off by several tens of meters. This is because the clocks in satellites experience less gravity than those on the ground, and therefore they'll run faster. This effect is known as gravitational time dilation. Newton's theory of gravity does not have any effect on the flow of time. But since Einstein's approach involves very difficult mathematics, a physicist will often use Newton's approach where possible. Only for very strong and extreme gravitational processes is Einstein's approach required. Therefore, it is known as a relativistic correction. However, whilst Einstein's general relativity works well on the macro scale, there are still problems on quantum scales and galactic scales. In spiral galaxies, the orbiting of stars around their centers seem to strongly disobey both Newton's law of universal gravitation and general relativity. Astrophysicists, however, have chosen to explain this away by assuming the presence of large amounts of dark matter, despite us still having no clue to what dark matter is or having a direct detection of it. Thus, it might be that both Einstein's general relativity and Newton's theory of gravity are partially right, but partially incomplete. Modified Newtonian dynamics, or MOND for short, was proposed by Mordechai Milgram in 1983. The motivation behind MOND is that Newton's laws have been extensively tested in high acceleration environments, such as in the solar system and on Earth. But they do not work for objects with extremely low acceleration, things like the stars in the outer parts of galaxies. MOND proposes a fix to this. At very long ranges, the strength of gravity should fall off at a lower rate than the one predicted by Newtonian gravity and general relativity. This would mean that the higher velocity of stars around the edges of galaxies could potentially be explained without the need for invisible mass dark matter. Again, visually, MOND looks very similar to Newton's law. Fn here is the Newtonian force, m is the object's mass, a is its acceleration. But we now have this correction term mu known as the interpolating function. The most common definition of mu is the simple interpolating function, which takes the form of the following. Here, a0 is a new fundamental constant, which marks a transition point between the Newtonian and deep MOND regimes. This allows us to reproduce the Newtonian result at high acceleration, but leads to a different behavior at low acceleration, known as deep MOND. Because when the acceleration a is much larger than the transition point a0, mu is approximately 1, and we recover Newton's law. But when the acceleration is much smaller than the transition point, we get the following. This then solves the problem of stellar rotation curves without the need of dark matter. There are so many different generalizations of MOND with different interpolating functions mu. However, so far MOND and its generalizations are not able to account for observed properties of galaxy clusters. It's really hard to introduce a new theory of gravity that agrees with all other correct predictions of general relativity so far. There is still room for a theory of gravity that agrees with all of our observations and even quantum scales, and many researchers are actually working on this. Who knows, you could be the next Einstein. That's all for this week's video. If you enjoyed it, please don't forget to leave me a like, share and subscribe.